One of the skills we learn in chemistry is how to determine if a single displacement reaction should occur using an activity series. If the equation does occur, then there are three forms of an equation that we can write: a molecular equation, an ionic equation, or a net ionic equation. The single displacement lab that you will have completed in chemistry will have asked you to do all of those things. So let's go with an example where we take a piece of aluminum metal and we're going to place that into a solution of copper 2 nitrate. Before we even begin that, we want to know, will this occur? So the rules are always as follows. If the solid, which was aluminum, I'm going to use a different highlighter color here, which was aluminum, is higher on the activity series than the metal that's in the solution, which in this case would be copper, then the reaction is predicted to occur, and a swapping of those metals should actually be what you see. So one of the things we'll do here is just write out the full equation for this reaction. Aluminum is more reactive, so we'll go ahead and put that down. And when placed in a solution of copper 2 nitrate, the copper from that solution will actually remove electrons from aluminum until the copper has gained back 2 electrons and become solid again. And as the aluminum is having its electrons stolen, it will become an ion and will dissolve into solution. So we should see copper forming a solid and then aluminum combining with the nitrate. Now, to do this, we have to remember that aluminum has a 3 positive charge and nitrate is NO3 with a 1 charge. When we go to write that out, then it would be AlNO3 3, and that should be in aqueous form. The reality is that this will actually be a situation where the aluminum ions and the nitrate ions will likely just float around in that aqueous solution. If we were to take out the copper solid pieces that will precipitate out and then evaporate all of the water, we would eventually be left with solid aluminum nitrate. That's just kind of information, background information, but not necessary to what we're doing here. The next step is, because what we're going to be doing right now is we're writing out the molecular equation. This is the equation you guys are used to writing. The next step is just to go ahead and balance that. So looking at that, I have 2 nitrates on my reactant side, but 3 on my product side. So I'm going to go ahead and put a 3 in front of the CuNO3 and then a 2 in front of the AlNO3 and then I'll go ahead and balance out my aluminums and my copper. Now that's the molecular equation, and that is what we are used to working with. The next thing I want to show you is how to write an ionic equation. Ionic equations essentially take all of the ions that are involved in the reaction and they break them down into their individual parts. This is probably one of the more tedious things in chemistry. So you take everything, if it's solid, you leave it as solid. So I'm going to write 2Al solid. If it is an ionic compound, which is, copper 2 nitrate's an ionic compound, we're actually going to break that down into its individual pieces. So we have copper ions and nitrate ions. We have 3 copper ions, so we'll write 3Cu, 2 plus, and because it's an ion, we're going to write the term aqueous after it. Then we have to figure out how many nitrate ions we have. Well, we actually have 3 times 2, so we have 6. And in these equations, it's important to write out the full balanced equation. So we have 6NO3, 1 minus, and again, it's aqueous. Continuing on in this equation, we have another solid, so we'll just write 3Cu solid plus aluminum nitrate, again, is aqueous. So all of these aqueous ionic compounds, we're going to break those down. 2Al, and aluminum as an ion has a 3 positive charge. And then we have a total of 2 times 3, or 6 nitrates, and that should match up what we had before. So we're going to write 6 NO3, 1 minus with the aqueous symbol there. This is called an ionic equation. So again, we're taking the ions in that equation and breaking them down. And now we're going to write the net ionic equation. And this is going to look familiar to those of you who have been kind of paying attention to the redox reactions we've been looking at. In order to write a net ionic equation, what you're going to do is you're first going to cancel out anything that's considered a spectator ion from the original equation. So spectator ions are going to be those species that exist on both sides of the equation and nothing about them has changed. So kind of moving through, aluminum is solid on this side but aqueous on that side, so definitely involved in the reaction there. Copper is aqueous on this side, solid on that side, so again, definitely involved in the reaction there. We have nitrate on this side in an ionic form, and we have nitrate on that side, also ionic, so we're going to go ahead and cancel those out. The net ionic equation then is just anything that we have left over. So we have 2 aluminum solids plus 3 Cu, 2 positive, and then 3 Cu solid, and 2 aluminum ions. The net ionic equation then is where we often are getting our redox equations. What's nice about this, because we started with the molecular equation, we went to the complete ionic equation, and now we have the net ionic equation, is that this is a redox reaction, but it's already balanced. So you wouldn't have to go through the half reaction method to get the numbers in front here. So normally we do the half reaction balancing of redox equations when we don't have the molecular equation to start off with. Let's do one additional thing, kind of a bonus review. What is oxidized and what is reduced in this equation? So we could easily answer that now by assigning oxidation states. So aluminum, because it's a solid and there's no charge on it, will assign an oxidation state of 0. We have an ion in copper 2 positive, so that is going to have an oxidation state of +2. Copper is then solid, so it would be a 0. And then aluminum's a 3 positive, so we'd have a +3. So when we just take a look at this, again, oxidation states are something that we've done before, and identifying what is reduced, what is oxidized, again, is something we've done. Aluminum is going from a 0 to a +3. And it very, very clearly, has lost electrons. So aluminum would be our lose electrons oxidized. And then copper has gone from a 2 positive to a 0. So copper was stealing the electrons or removing electrons from aluminum. So copper would be our reduced element. The only other thing I would say is we could go back then to the original molecular equation, and we could look and identify what is the reducing agent. And what is the oxidizing agent. Now, notice I was really purposeful in how I wrote that, so I know that whatever element is oxidized, whatever that is a part of, that would be the reducing agent because it is causing reduction in another element. And then with the copper, which we know is reduced, that is going to be the oxidizing agent because it is causing oxidation in something else and is therefore reduced. So if we go back and look at our original molecular equation, aluminum was just by itself. And so aluminum itself will be the reducing agent. So I'll go ahead and put just Al solid. And then as far as copper is part of that CuNO3 too. So the oxidizing agent is CuNO3 or copper 2 nitrate. So CuNO3 aqueous would be our oxidizing agent. Okay, hopefully that helps you. Again, I'll be available in class to kind of walk you guys through things that you get stuck on. Basically, predicting single displacement reaction, you'll have had lots of practice with that in lab, lots of opportunities to see when that does occur, when it does not occur, and a lot of practice just making those predictions about the new things that are formed, and you will follow up by writing out molecular and net ionic equations. I'm not asking you guys to write out the full ionic equation, though you could, and then just simplify that down to get your net ionic.